plateaued, you know, decades ago and sits here. And so that's the first generation of X-ray devices. The second generation was to use relativity, which is what synchrotrons are doing. So synchrotrons are taking that electron beam that melts your copper anode and accelerates them to relativistic energy, and all those X-rays that are emitted, if you go through a magnetic field, are now emitted in the forward direction in a narrow cone and a narrow bandwidth, and it's much more powerful. And so this is going from a brilliance of about 10 to the 9th in the usual units to about 10 to the 21 with today's synchrotrons. And I just added, I've had this plot for a long time, but I just added this little MBA for multi-band achromat, these so-called ultimate storage rings now have gone up about 2 orders of magnitude. We thought the synchrotron performance had plateaued. They've done some clever things with their magnet arrangements, and they've gotten a bump now where they're up another couple of orders of magnitude. And so that's all really due to relativity. So that's the second generation of radiation sources. And as you all know, tremendously productive scientifically, many thousands of users around the world. But you have to go, they cost $1 billion, and you have to go to a national lab to use them. And you know, many countries don't have them. And now, more recently, with LCLS turning on, and SACFA and XFEL coming, and PSI, lots of X-ray lasers coming. This is what I've spent most of my career designing, are FELs. And we've gone up another 10 orders of magnitude in brilliance. I'm switching here from average brilliance, which is the real measure for synchrotrons, to peak brilliance, which is a better measure for FELs. You could make an FEL with the same rep rate as a synchrotron, a superconducting FEL, but all you would do is cut holes and things that would be that interesting scientifically. So it's really the single shot brilliance that matters for FELs. That's up about 10 orders of magnitude. And so that depends on coherent emission. Coherent, people use coherence in a lot of different ways, colloquially. We even say that the synchrotrons are coherent X-rays. But what I mean by coherent is that the electrons act together to emit the wave coherently. It's a coherent source. It's not just that the resulting X-rays have some fraction that are coherent, but they are emitting in phase. In a synchrotron, in an undulator, the electrons are just randomly arranged. They're not in phase at the X-ray scale, and so there's partial destructive interference. And the result of that is that the power goes as the square root of the number of electrons that are emitting because of this interference. I'm sorry, the power goes linearly with the number of electrons. The electric field goes as the square root. And in XFELs, because they're in phase, they're constructively interfering, it goes as the square. We've got about 1 billion electrons in a pulse, so it's about 1 billion times more powerful. And then it's that scaling that gives you this enormous jump. So those are the three sources. Small sources, very useful, great history, but they're really doing a different kind of science than you're doing at synchrotrons and now at FELs. And it's quantitatively different, it's qualitatively different too. One way to think about it is this 10 orders of magnitude difference. It's the difference between having an abacus and a teraflop computer, a supercomputer. It's really the same. You're just simply not going to do the same kind of work you do with one with the other. So what we're trying to do, and XFELs obviously are also at the billion-kilometer length scale, so they're big things. We're trying to we're trying to shrink that size. And so we do that by moving into the 21st century from the 20th century. In the last century, what we used to make X-rays were magnets, permanent magnets or electromagnets, and they have a period of a few centimeters. And so electron beam comes in here. If the undulator period is a few centimeters, and there's a resonance equation, which is partially given here. I don't know where the rest of it is. But this should be lambda sub-x, lambda sub-laser over
something.
Is this all gonna, is this,
You lost degree.
We're gonna-
4 gamma squared.
we're gonna have a problem if this
You
continues.
lost degree.
Yeah, oh well. It takes a few GeV beam. That's why we have, the only reason we have big accelerators is because we use centimeter periods, that we have magnetic fields that are consistent with that to hit this resonance equation. If I want to make 1 angstrom X-rays and have a few centimeter period, then I need a few GeV electron beam, which means I need a kilometer of electron Linac. So an alternative to that is to do the same thing. Have your electron beam interact with a laser field. It's just an electromagnetic field. In fact, to an electron, if you're an electron coming toward this undulator, which is a static magnetic field in our reference frame, in the electron's reference frame, it's actually a propagating electromagnetic wave. It looks just like a laser field coming at it, but it's got this long period. So if we use a real laser field, a real electromagnetic wave propagated toward the electron beam, it's got a 1 micron period. That's a difference of 10 to the 4 from the centimeter period of the static undulator. And so there's a gamma squared here. So we can shrink our electron beam energy by a factor of 10 to the square root of 10 to the 4th, or a factor of 100. So we go from roughly a kilometer to roughly a meter in length. It's the various numerical factors give you that additional bit. And so suddenly we've got a much smaller, more affordable device. There's always trade-offs with this kind of thing, and we'll talk a little bit about them. So this is what we're building schematically. There's an RF gun, which is roughly the size of your fist. It produces a very bright electron beam, and then about 1 meter of Linac. And that's it for the accelerator. So it's just over a meter long. And that looks very much like the front end of one of the big XFELs. It looks just like the first meter of the XFELs. They make our best electron beam, so we're taking the front end of that, making our best electron beam, and then interacting it with a laser. We have to focus the electron down to a very small size. This is one way to think of this as a scattering experiment with the laser photons, and so we want to have both the laser beam and the electron beam focused as tightly as possible to have a dense target to make lots of X-rays that come out. I'll say at times that this is ICS. This is inverse Compton scattering is the terminology for this type of X-ray scattering, or backscattering of laser photons into an X-ray beam. It's like undulator radiation in many senses, and I'll say that the performance of this device in the current implementation is similar to a bend magnet, a synchrotron. It's not as powerful as an undulator beamline, but it's quite similar to a bend magnet beamline. But that's an oversimplification too, because it's a different type of beam. It's got very short pulses, sub-picosecond pulses like an XFEL, not a lot of photons, about 10 to the 7th to 10 to the 8th photons per shot. And then it depends on how high a repetition rate you can have with your machine. And we focus it to a few micron spot size. It's a round spot, so it's not asymmetric, it's round. And the X-rays come out and they have a fairly large divergence, about 10 milliradian divergence. The product of the spot size and the divergence is small. It's not that different than a synchrotron, but it's a different format in that it's coming from a very small source into a large divergence angle. With optics, you can convert that into a more collimated beam that's a larger size, but all these things involve trade-offs. And you see this, I've marked the size there, it's about 4 meters long in its shortest version. And so here's a version of that. These are all accelerator things that are in here, but we start with the gun, we go through some diagnostics. Our Linac is 1.4 meters long exactly, and then we have some quadrupoles that focus to a very small spot here. The ICS laser, the powerful laser, comes in and crosses it and then goes back out. And then we need an optic very close to that to capture this diverging X-ray beam and bring it through our shield wall. So we try to collimate with that first optic. Meanwhile, the electron beam is bent away from the X-ray optic and then dumped down into the floor in this case. And so this is what we're building it. Actually, we're building it at MIT. An ASU team is building it. It's an ASU device. But they have very graciously agreed to build us a new building at ASU. And while we wait for that to happen, we're building at MIT with my old colleagues. That's where I came from. They have some unused shielded space that we're building it at. And so we expect to have this operational in spring of next year, less than a year from now. March, we should have this operational making X-rays. Okay, so this is the basic machine layout. Should have mentioned I'm going to talk about two machines today. This is the first one we're building. The technical risk here is pretty low. It'll work. I hope it will hit our targets, but even if we don't, it'll certainly produce X-rays. There's no question. We have a scheme that I'll get into in a moment to convert this into an XFEL, and it involves adding some equipment to this existing machine, and then we get XFEL-like performance. Still not as powerful as the big machines. This just doesn't have the stored energy that the big machines have, but it can be fully coherent, and in some important parameters, actually outperforms the big XFELs. Okay, so I'm just going to quickly tour through the technologies that are going into this thing we're building. Then I'll talk about some of the applications of the X-rays, what we can do with this that you can't necessarily do with a synchrotron, and then we'll get into the coherent machine, the XFEL. This is showing the gun. So this thing is about, I think it's 6 centimeters long. It's very short. This whole thing is about 20 centimeters long. This is a gun surrounded by a solenoid. This is really more of an accelerator slide, but it's essentially a disposable photo injector. Normally, a photo injector costs $200,000 to $300,000 because of how it's built. It's complicated. It's got a replaceable cathode. They have to tune. There's lots of things that make it costly. Ours is just 6 pieces of copper that are brazed together, and if we damage it, which inevitably you do eventually, typically with the laser on the cathode you damage the thing, but we'll just throw it out and put a new one in. We think we can produce this for about $10,000, and so if we ruin one a year or something, it's okay. It's replaceable. The whole thing is replaceable. So we think this is a very inexpensive, kind of elegant design. It's vastly simplified from existing guns. A similar thing, and this is being designed in collaboration with people at SLAC and in a private company. Valery Dolgoshev is a well-known RF designer. Same with the Linac. Sammy Tintawi's head of the advanced RF group there, and we're at SLAC, and we're using his latest design. He's just got this thing working now. Usually accelerators are, again, expensive things with many braze operations. They're stacked up disk and washer structure. But this is built in 2 halves. So you can NC machine the entire thing and in 2 halves and then braze them together in one operation. And there's no stack up, there's no multiple pieces, there's no lengthy measuring process. So this is a much less expensive yet high performance accelerator. We think this is a really nice solution. RF frequency is 9.3 gigahertz. That doesn't mean too much, but it can operate at up to 1,000 hertz. So that's the kind of natural pulse arrival rate is up to 1,000 hertz, the X-ray beam too. We need powerful lasers. There's 2 lasers. We're buying both of them commercially. One is for the photocathode excitation. That's a short pulse laser, about 200 femtoseconds and a millijoule or so. And then the ICS laser, this is coming out of Trumpf in Germany. They make these enormous kind of 10 kilowatt welding metal cutting lasers, and they've just recently spun off a scientific division, and so they're applying their industrial technology now to a scientific laser. So it's 200 millijoules and a kilohertz, so that's a 200 watt average power laser. It's a very powerful laser. I think it's the most powerful commercial laser you can buy, a commercial short pulse laser. So we're have these in next winter or so. And you can see, you know, I'm working with the national lab. You know, how can ASU build a particle accelerator and an X-ray light source? And this is how. We work with the national lab on the accelerator structures, and we work with the modern laser manufacturers. These are also not twiddle things. It drives me crazy when, you know, somebody's got to have their fingers on the laser mirrors all day to make it operate. But these are fully industrialized units. Talking to customers of this one in particular, it runs for weeks at a time without being touched. So this is a machine that's designed to operate 24/7 and be extremely stable. We're looking for synchrotron-like stability out of this device. By being small, we can pursue that. There's some subtle benefits to this that aren't immediately apparent. You know, if you want to upgrade SLAC, you've got to upgrade, I don't know what it is, 500 klystrons or something. Nobody's got the money, you know, it's hundreds of millions of dollars. But we've got kind of one of everything. It's a complicated machine. It's got one of everything that SLAC's got 500 of, but it's got the same, you know, variety of stuff, lasers and RF power supplies and accelerator structures, all these things. Complicated technology, but when new technologies come along, we can take advantage and quickly upgrade. So we've got I'm not even going into it, but the RF power supply, which is really the thing that determines your stability. The accelerator itself is just a hunk of copper. It stores energy. But the power supply is the key thing. And because we have just one to power the entire accelerator, we can really focus very carefully on that one. So we're looking at the specs on it are about 15 parts per million stability, which is a factor of between 10 and 100 better than the typical accelerator power supplies. So I anticipate that we'll have a very stable machine. Putting the numbers together, we're looking at kind of 10 to the 10th to 10 to the 11th photons per second, coming in these short bursts of about a half picosecond pulse length. And so here's some average numbers. Average brilliance is about 10 to the 12. It depends. We're naturally a fairly wide bandwidth. If you're doing pink beam experiments or imaging experiments where you can accept a wider bandwidth, then we have more photons and higher brilliance. But if you're doing crystallography, you need a narrow bandwidth, and we're going to give up some flux in order to get that. As I say, the source size is very small. It runs around 3 microns, 2 to 3 microns, RMS, that is. And the divergence angle is quite large. RMS of 3 milliradians means kind of 10 milliradian opening angle, really. And there you see the photons per pulse number. Any questions before I move on from this one? John?
Is the lab at ASU long enough so that when you bring this beam divergence down to 1 milliradian for crystallography, the sample will be in the same room? That would be a bit of a disaster if it wasn't.
The sample in the same room as the machine. You don't really, I don't think, want anything in the room with this machine.
Okay, so we own this. You're going to have optics to bring the beam divergence down to the crystallographic value.
Yes.
Say
Yes, yes.
And you own the real estate where you put the sample for that.
That's right. We have to come through a 4-foot thick shield wall. So we have to capture the beam and collimate it, bring it through the wall, and then, you know, manipulate it for the particular experiment, whether it's collimated for crystallography or focused for imaging.
The focus would not be the other end of the building.
No. Other questions?
With a big brilliance, you are 12 orders of magnitude below the present XFELs.
Yes, this is not yet the XFEL.
Okay.
We'll get to the XFEL.
Okay.
Yeah, so this is comparable to a synchrotron, but a short pulse synchrotron. It has better numbers than the slicing experiments. If people have looked at doing the slicing at a synchrotron, we've got more flux, shorter pulses than that. So I just want to mention a few applications. So the applications are, I think we'll come to new ones as we understand the source properties better. As I say, it's not an XFEL, it's not a synchrotron, it's certainly not an X-ray tube. And so the science has been optimized for each of those devices. And as we start to use that, I think we'll optimize our science for this. I'll say what we can see. I'll say what we can see right now, looking ahead. One is to have it in medical centers where we can use its partial coherence. It's partially coherent in the sense that a synchrotron is, to do phase contrast medical imaging rather than absorption radiography. And that shows a lot of promise for detecting differences in soft tissue. And it's also, it's predicated on the photons, on essentially phase shifts as the X-ray wavefronts propagate through your body. So it does not depend on being absorbed in your body, which is dose. All we need to do is measure the interference patterns on the detector. So it's possible that it will lower the dose as well. But it'll certainly give us contrast on things that have the same density. Basically, our bodies are there's not much density difference between, say, plaque on an artery wall and the wall itself. So this is showing a conventional micro CT image of a plaque on an artery, and you can see some structure, but not much, and it's greatly enhanced in the phase contrast structure. And it's not my specialty, but when we talk to the radiologists about this, they're very excited about it because there are a number of different types of plaque, some at danger of coming loose and causing a heart attack, some are encapsulated and pose no danger. There's no way to see that today, and this would conceivably allow you to do that. This is showing images of a tumor in a breast, showing attenuation contrast on the left, where not much is visible. Phase contrast showing differences between the tumor's tissue and the healthy tissue, and then histology confirming that. And so you just can't see the difference in tumor and healthy tissue with this. And so one of our first experiments with this, we're working with a couple of radiologists from the Mayo Clinic, and when they excise tumors, they have to get good margins. They have to take out enough that they have healthy tissue all around the margins. And that's a difficult process. They actually remove the tumor, the patient goes home, they slice up the tumor, and then they look at it under a microscope. And if they didn't get healthy margins, you have to go back into surgery. And this happens with about 20% of patients. And so with this, we could bring that tumor. We don't even have to put the patient into the machine, into the X-ray beam. We can put the tumor whole, unsliced, into the X-ray beam and look at its margins and have just a single surgery. So this is one of the early experiments that we'll be doing, working with both Mayo Clinic and Mass General. Another experiment is small angle scattering for semiconductors. The semiconductor manufacturers, Intel, can't see what they make now. And their conventional methods of measuring it have run out of resolution. By using small angle scattering, they're able to reproduce, the modern chips look like cities, essentially. They're very three-dimensional structures and they're repetitive. And so looking at diffraction patterns, they can reproduce features on the chips and resolve them. And actually, of course, with diffraction, the smaller the features get, the better we can resolve them, the more diffraction we get. And so semiconductor manufacturers are very interested in having this in their fab plants. They'd actually have the machine in the fab, measure the things in situ. Same thing with the hospital medical imaging. These are all things we can't do with a synchrotron, is when you can bring the x-rays out to where the science is happening, the medicine is happening, the industry is, it changes things. This is Thea Salling of Maersk Oil is looking at the structure of oil-bearing rocks. This is in Qatar, where it's illegal to take a rock out of the country. And if they can get, they have all these pores and they unlock some fraction of the oil that's in there, but if they could unlock 1% more, it'd be, it's some economically enormously valuable breakthrough. But they can't resolve that now with the X-ray machines in the country. So with a much higher resolution, they'd be able to look at these things. Okay, biosafety level for proteins, viruses. you can't bring these to APS, and so you need that machine in your lab. So I'm giving lots of examples of places where you have to bring the X-rays to the device. We went to the Louvre a few years ago. They have a complete scientific lab in the basement, and on Mondays when the museum's closed, they bring their artifacts down there, the paintings and so forth, and study them. And so they're looking to put a powerful X-ray machine in the basement. They have an ion source down there and various analytical equipment. About 200 scientists actually down there. Okay, so that's examples of how even that was all for the incoherent machine. That's basically some of the scientific case that we would have. And now I'm going to talk about how we make this coherent. How do we build this, to convert this thing into an XFEL? So that's all that is kind of a given. That'll work at some level. What I'm going to describe now is a little bit more interesting and technically risky. This has not been done yet. The inverse confidence scattering has been done. We're trying to make it a useful scientific tool, but there's no mystery about the physics. So the incoherent sources, whether this is showing a bunch of electrons arriving in an electromagnetic field, could be a static undulator or a laser. And there's no patterning to them. And so their wave trains of X-rays that each emits are out of phase, and the intensity goes as just linearly with the number of electrons. The FEL, the free electron laser instability, that's what it is. It's an instability that exponentially grows. It starts from shot noise, from small variations in the density of the electrons, create a little bit of more or less X-ray power, and those variations cause the electrons to move relative to each other. And over that 100-meter long undulator, what's happening is they're arranging themselves into short bunches that have a period at the X-ray scale. If you want 1 angstrom X-rays, then your electrons have to be, electrons here, and then 1 angstrom away, another set of electrons. And so they get grouped, like in the bottom picture is shown, they get grouped like that. Because they start from noise, they essentially amplify those noise characteristics, and that's what SASE radiation is. SASE is self-amplification of spontaneous emission. A spontaneous emission is just the shot noise effect in the electron beam. Actually, it's an interesting thing. If electrons were a fluid, sometimes we model them as a fluid, but if it were a smooth fluid with no particles, there would be no synchrotron radiation. It's the only reason we get radiation out is that shot-like character of them. Okay, so that's how SASE machines work. But it's not the only way to get bunches of electrons. Here is something showing electrons bunched too. This is an electron microscope photograph, and we're seeing light and dark areas, and that's a density variation in the electrons at the X-ray wavelength scale. So when I gave this talk a few years ago to people at SLAC and the other FEL places, the accelerator physicists would all say, Graves, you're nuts, because everybody knows it takes a few GeV electron beam to support, X-ray wavelength, X-ray density modulation at X-ray wavelength. But no, you can do it at a few hundred keV. It's doable. Right? You just have to combine these techniques. And so that's what we're doing. We're looking at using electron diffraction in a crystal to pattern our electron beam at a small scale, not quite this small yet, and then do some manipulations. This is, of course, a spatial modulation. By spatial, I mean transverse to the direction of motion. But there's a sophisticated electron manipulation we can do called Emittance Exchange, which has been demonstrated. And that swaps the spatial dimension, essentially the phase space of one spatial dimension with the longitudinal dimension. That means we can take a spatial modulation like that and convert it into a current modulation, which is what you need for coherent emission. And so we've done now a number of studies, looked at the physics of this. I figured it'd fall apart, but it hasn't. It looks like it'll work. And so I'll just say a little bit about how it works without equations. So what we need to do is produce these short bunches of electrons, where there's electrons and then a space. I don't know if I can do this without a quick. Okay, so here's how we do it. We diffract through a crystal grating structure. We have the electron beam come through in here, and if the height of the ridges is set so that essentially all of the beam is diffracted into one of the low order Bragg peaks, so that's the extinction length of that particular peak, and the grooves are much shorter than that so that the primary beam passes through, then downstream of this, we'll have an alternating pattern where some of the electrons will diffract at some angle, the Bragg angle, and some will proceed straight. If we then block one of those beams, it could be either one, and image the grating. Now we need to use electron optics to image the grating. Then we'll reproduce that structure, and this is what a simulation of that looks like, where we've now thrown out roughly half of the electrons that were in the grooves or were in the ridges and kept the straight ahead beam. And so now we have a spatially modulated beam. This modulation in this case was at 150 nanometers. So this is showing the Fourier transform of that. And I may refer to this bunching factor. Bunching factor is telling you how well your electrons are arranged at the wavelength you're interested at. We use it in FELs all the time. A saturated FEL has a bunching factor of about 0.6 or so, and we're getting there. We're over 0.6 here. We want to shrink this modulation spacing down now by a factor of about 100 in order to get to X-ray wavelength scales. And we can do that using a couple of mechanisms. One is that, we're re-imaging, we have to re-image the grating so we get our density modulation. Well, we don't have to do a one-to-one image. We can demagnify that dramatically. A factor of 100 is not a big deal for electron optics. We actually do about a factor of 30. So all we have to use is quadrupoles to de-image, to demagnify that and re-image it. And then in the process of swapping it into the longitudinal plane, we get an additional demagnification that occurs to bring us, in this case, we're aiming for 1 keV photons, or about 1.24 nanometer modulation. The key thing about, one of the key ideas here is that we can entirely diffract the primary beam so that none of it comes into the 0th order, none remains. And so we did, just a couple of months ago, we did an experiment with SLAC's ultra-fast electron diffraction facility, an experiment where with a thin silicon crystal, this is now flat, it doesn't have the grating spacing, so it's going to diffract all of the electrons or not. As we tune the angle, we go from all of the beam coming through, this is about a picocoulomb of charge, which is what we're looking for, all of the beam coming through to meeting the Bragg condition, and we knock out all of that primary beam. It's all diffracted into a low order peak. So that's the basic idea of this. And now we just have to transport that and do our manipulations on it. So this method doesn't rely on any plasma accelerators, laser accelerators, anything too exotic. We just have to use electron diffraction and use these other components that have already been demonstrated to convert. I think I have to go into that one. So I just say a few words about emittance exchange. This is a very strange thing. If you think of a light beam, it's like you could take the spot size and divergence of a light beam and convert that into its pulse length and spectrum. And so it's not possible with light, right? We can't make that conversion, but we can do it with electrons, and it's called emittance exchange. And we do it with a set of dipole magnets and a particular type of RF cavity. So it's just getting the right combination of these components in order to do it. So we take, in the XY space, we take our set of beamlets that we've generated by diffraction. Meanwhile, in the time, I'm showing time and current here. So there's no pattern at all in that. The beam is not modulated longitudinally. And then in the phase space, we have all these little beamlets. X and X prime is our angle with respect to the axis, dx, dz. And the time energy phase plane, there's no pattern. We go through this set of magnets, and I'll say just a little bit about them. And we exactly swap these. You can't partially do this. You can only 100% do it. And so we take our energy time distribution and put it into our transverse. And likewise, we take our transverse distribution and put it into the longitudinal. And voila, we have our short bunches. And this is just exactly what we need. I got this idea by thinking about nanotip emitters in a cathode, which people have really liked for a long time, because from a single tip that's a nanometer in size, you can get an extremely bright electron beam. Of course, this is how the field emission tips. This is how electron microscopes work. But if you combine many of them, there's a theorem called Liouville's theorem that says you can't take out the dead space in that distribution. If you have tips that are 1 nanometer, but there's 10 microns or 1 micron between them, all that dead space counts in the emittance, which is the total phase space volume of the beam, and it's killer. You can't take it out. Those tip. If you combine many tips, it's actually no brighter than a flat cathode. And so I was thinking, wow, what can we do with that dead space? And then it occurred to me, well, the FEL's got dead space. It's the space between the bunches. And then the Emittance Exchange thing is a way to use that. So essentially, we're beating Liouville's theorem here by using the dead space in a clever way. All right, we don't have to go too much into this, but this is showing what it takes. It's very simple. This is about 3 meters long. This beam line is 2 dog legs, which consist of dipoles, and then a deflector cavity and a single accelerating cavity. These cavities together are about 20 centimeters long. It's a very short device. And by doing that, we couple X and Z. So in the matrix transport we normally use, usually your on-axis, your on-diagonal submatrices are non-zero, and the off-diagonals are 0, which would indicate no coupling between X and Z. And we exactly do the opposite, where we're able to zero these and have finite values in these off-diagonal elements. And we've shown that we can do this with a ratio about 10 to the 4 between the transverse and longitudinal, which you need this huge ratio to get to that X-ray scale. So it's not a different machine than the first machine. This is showing something I showed at the beginning of the talk, but now with this 5-meter section inserted in. About half of this does the imaging of the crystal grating, which would be up here just after the gun. So we're taking roughly 4 MeV electrons and diffracting them. They're very high energy for electron diffraction, but there's no problem with that. That's what we did at SLAC, in fact. And then we image the grating with half of this beam line, and the other half would do that emittance exchange. Yeah, that's all I'll say on that. So if we do all that in simulation, we start with 1 picocoulomb, we get about 1/3 of that picocoulomb. This is very low charge, but that's what we're limited to, I think, for various reasons. We get about 1/3 of that through all of our transport, and we get still very good bunching at our 1 nanometer. We had this 1 keV photon energy aim. And I can run numerical simulations of that and compare what we call our compact XFEL time profile, which is it's something like 20 or 30 femtoseconds long, and its spectrum, which is a single spike, with SASE. This is at a different wavelength, but I just used one of my old SASE simulations here with its the typical spiky profile. So something that's not obvious is we're not dependent on the shot noise. We're not dependent on the SASE profile. We're doing the same thing every time. We have these ultra-stable power supplies. We're deterministically setting our beam pattern. We can make that diffraction grating have a fixed period. It could have 2 periods. It could have a chirped period. It could have biperiods. It could be, you could make two colors that were not only were they synchronized perfectly, they were actually phase locked. They would be phase locked relative to one another. And you get rid of all the noise is gone. There's, you know, we're just not dependent on noise. It'll be ultra stable. I'm telling you all the good things. There's a couple of bad things. One is that it's, let's wait a second to get to that. It's still our small machine. It just doesn't have the stored energy. We're still looking at about 10 to the 8th photons per shot. It's not that much more than the incoherent, because we've had to drop the charge very dramatically in order to get this very fine scale structure on the beam. But it's fully coherent. It's coherent in all dimensions. And so the brilliance is very high. So its flux is relatively low, but the brilliance is high because the phase space is so small. And that deterministic shaping of the beam, you know, we can actually control the phase fronts with this, enables interesting things. Now, one would be to make a chirped output beam and then use X-ray optics to compress that. Use a graded multi-layer. I think we could compress below a femtosecond. I don't see why we couldn't. So you could conceivably have attosecond hard X-rays, you know, single spike spectrum with this. Really enable new science. Okay, so now I'm putting both of these machines on our original plot. Our tubes are down here. We're about 4 orders of magnitude brighter than a tube. We're still, you know, well down. This is the incoherent machine, well down from the synchrotrons. And then the coherent machine has an average flux that's only a couple of orders of magnitude off of the synchrotrons. Not flux, I'm sorry, average brightness. It's about 10 to the 18th instead of the 10 to the 21 number. And the peak is still below, you know, LCLS is at 10 to the 33. We get about 10 to the 29, about 5 orders of magnitude below, but way above the synchrotrons. And that single brightness or flux number hides a lot of stuff. It doesn't say anything about your stability, you know, your stability and your time profile and your focusing, pointing, and spectrum. So this would be an extremely stable machine. The other thing is, of course, this doesn't, you know, the FELs, you know, is the Korean FEL turns on and SECLA is on and PSI comes on. They're all, the risk is low. We know that FELs basically work. We're kind of where LCLS was in the year 2000, where we were all worried to death whether it would work or not. But we should know, I think in about a 3-year time span, we'll do the R&D to prove these ideas out. Various parameters. Just wanted to say quickly, yeah, I've got time, what our project schedule is. So we're now building the incoherent machine at MIT Bates Laboratory. We'll finish building the accelerator by the end of this year. We have to wait a little bit for our laser, but we'll be making X-rays in spring of next year. And so we'll have a program at MIT for about 1.5 years or so, and then move the machine to ASU when our new building is ready. So this is showing the new Biodesign C building that's under construction. I don't know if they've started yet. They're due to start this month. John's saying yes, they have started. Good. So hopefully we're on schedule with that. The basement of that is where this is going to be situated. There's these two colors are showing two completely independent labs that can house 2 of these things. So our idea is that we can have our incoherent machine in one and our upgrade CXFEL in the other one. And various support laboratories. So again, the schedule. And here are the folks that are involved and who we've had support from. So it's a multi-institutional collaboration. Thank you.